Good afternoon. I'm very happy to have Dr. Koichi Okuda here to share us with phantom experiments using iodine 123 MIBG. I believe he has plenty of experience of using this phantom across the Europe, Japan, and Taiwan. And now let's welcome him for the talk.
Hello everyone, I'm Koichi Okuda from Kanazawa Medical University, Japan. I would like to thank the Nuclear Cardiology and Neurology Taiwan Society of Nuclear Medicine and Dr. Han Xianbin Shoshuan Memorial Hospital for inviting me to speak here today. My presentation is about iodine 123 MIBG phantom experiments in Taiwan, Europe, and Japan. Here is a brief outline of my presentation. First, I will present iodine 123 MIBG imaging and quantitative index of MIBG images, HER2-mediastinum ratio. Second, please let me introduce our acrylic phantom for MIBG imaging. Third, by using this phantom, multicenter MIBG phantom experiments were performed in Taiwan, Europe, and Japan. So I will introduce these results. Here is a background of MIBG. Iodine 123 meta-idobenzylguanidine MIBG is an analog of noradrenaline. In sympathetic neurons, MIBG characteristics of storage, transport, and reuptake are similar to noradrenaline. MIBG allows the visualization of cardiac sympathetic nerve activity. Cardiac scintigraphy with MIBG has played important roles in the evaluation of heart failure and neurodegenerative disease in cardiology and neurology, respectively. MIBG imaging procedure is as follows. After injection of 111 megabecquerel MIBG, early prana or SPECT or both images are acquired at 15 to 20 minutes. Then, delayed imaging is also performed at 3 to 4 hours later. Early images reflect the density of the cardiac sympathetic nerve terminal. Delayed images reflect both that density and washout of MIBG. The HER2-mediastinum ratio, HMR, has been used in prana MIBG images to evaluate cardiac sympathetic nerve activities. The HMR is calculated at the average MIBG count in the cardiac region of interest, divided by that in the mediastinal region of interest. Regarding region of interest ROI setting, cardiac ROI is set as circular or polygonal shape. We recommend slightly small delineation of cardiac shape. Mediastinal ROI is set as a rectangular shape at the upper mediastinum. Mediastinal ROI size and positioning greatly influence HMR variation. To overcome the differences in cardiac and mediastinal ROI settings, we have developed semi-automated ROI setting software called Smart MIBG. Please let me introduce this software in this video. First, early and delayed prana images are imported. Next, we move cardiac circular ROI to the center of the heart. Consequently, mediastinal ROI is automatically delineated at the upper mediastinum. We can modify the size of cardiac ROI. Then we adjust the ROI position in the delayed prana images. Finally, we can get early and delayed HMR values as well as washout rate. Still, there is considerable HMR variation due to differences in the characteristics of gamma cameras and collimators. Here you can see two photos, gamma camera system and collimator. Collimators are set in the front of the gamma cameras here. Gamma cameras accumulate counts of gamma photons. HMR variation are caused in scintillator materials and material sizes. Collimator conveys only gamma photons traveling directly along the long axis of each collimator hole. HMR variations are caused from collimator characteristics. I will talk about this HMR variation in the next slide. Here you can see some pictures represented HMR variation due to the characteristics of collimators. These are X-ray images of two collimators, low energy high resolution type and medium energy general purpose types. When the patient underwent prana scintigraphy using two collimators, HMR values showed different 2.0 and 2.6. This is because iodine 123 radionuclide has 529 keV high energy photons. This high energy photon can easily penetrate septa, black ones, in low energy high resolution collimator condition. However, in MEGP collimator, a part of high energy photons stops in the thicker septa. To overcome these HMR variations caused by collimator, we have developed a standardization method for the calibration of HMR using a dedicated phantom for MIBG prana imaging. MIBG calibration phantom is designed for prana imaging, and it can mimic prana MIBG distribution in the heart, mediastinum, lung, and liver and thyroid gland. The MIBG phantom is a flat structure with acrylics. Width and length are 380 mm each. Depth is 50 mm. This is a transaxial image of the phantom. All organ parts are connected as one compartment, so radionuclide concentration adjustment is not required for each organ. Moreover, the radioactivity of each organ is adjusted by changing acrylic thickness. Here, I would like to explain the structure of calibration phantom using the animation. This is an acrylic plate. Next, Basal layer shows background activity. Yellow area is filled with MIBG. Second layer shows cardiac, pulmonary, and hepatic activities. Third layer shows cardiac and hepatic activities. And the fourth layer shows hepatic activity only. Finally, we can evaluate different activities in each organ to modify the thicknesses of these layers. We can simultaneously prepare anterior and posterior views of the phantom images, then get two HMR values from one phantom. Theoretical HMR values are 2.60 and 3.5 for anterior and posterior positions, respectively. Cardiac compartment is set at the same depth in the anterior and posterior positions. However, the depth of mediastinal compartment, yellow ones, is different at anterior and posterior views. So we can calculate two HMR values from one phantom. How to obtain calibration factors from phantom images? Now I would like to show an example. By using the both flat size of calibration phantom, anterior and posterior images are acquired. After that, we compute two HMRs, 2.12 and 2.56, and then calculate average HMR values, 2.34. Since theoretical HMR values are already known, we also calculate average HMR value, 3.10. Next, we put 2 points at coordinates 3.10, 2.34, and 1, 1. As for the coordinate 1, 1, if we use the flat phantom, the measured and theoretical HMRs will be always 1. Finally, a calibration factor called conversion coefficient is defined as the slope of a line. In this case, conversion coefficient is calculated as 0.65. Next, how to convert standardized HMR? The HMR from institutions, HMR INST, can be converted into a standardized HMR STD using the following equation. HMR STD is equal to conversion coefficient STD divided by INST times HMR INST minus 1 plus 1. Conversion coefficient for institutional camera colorimeter system is determined by the phantom scanning, and the standard conversion coefficient is defined as 0.88 for MEGP colorimeter condition. In other words, all institutional HMRs will be adjusted and unified to a standard gamma camera with a MEGP colorimeter condition. Here is a validation study for HMR standardization. We used two normal patient groups for evaluating the standardization. These patient groups were created by the Japanese Society of Nuclear Medicine Working Group. The number of patients were 14 and 16 for hospitals A and B, respectively. As for the gamma cameras and colorimeters, prism ILIX with LEGP collimator was used in Hospital A. ECAM with LMAGP collimator was used in Hospital B. Conversion coefficients were 0.63 for Hospital A and 0.83 for Hospital B. By using this equation, we calculated clinical HMR values with or without standardization in two hospitals. Without standardization, average HMR values were 2.43 and 2.75 for hospitals A and B, respectively. Significant difference was observed between two values. After standardization, average HMR values showed no significant difference between two hospitals. The important point here is that standardization is necessary to compare HMR values between hospitals. So, let's move on to the next topic regarding multi-center MIBG phantom studies in Taiwan, Europe, and Japan. 36 hospitals and 30 and 781 hospitals have been participated in Taiwan, Taiwanese, European, and Japanese studies, respectively. In Taiwan, 156 phantom scans were performed in 36 hospitals. We greatly appreciated many participants. 56 gamma cameras and 127 collimators were used in Taiwanese MIBG phantom study. The gamma cameras were manufactured by GE, Philips, Siemens, and Spectrum Dynamics Medical. Some cadmium zinc telluride type gamma cameras were included. So we excluded these data from the following analysis. Since many types of collimators was used in Taiwan, we classified these collimators into 5 groups: low energy high resolution type, low energy general purpose type, extended low energy general purpose type, medium energy general purpose type, and medium energy low penetration type. Mean values of conversion coefficients were calculated in 5 collimator groups: 0.53 for LEHR, 0.59 for LEGP, 0.80 for ELEGP, 0.96 for MEGP, and 0.99 for MELP were obtained. Significant differences were observed in all combinations except for MEGP and MELP conditions. Since LEHR, LEGP, and MEGP collimators were manufactured by 3 vendors, we assessed vendor difference. In LEHR, LEGP, and MEGP collimators, the average conversion coefficients showed 0.52 to 0.56, 0.57 to 0.60, and 0.95 to 0.98, respectively. There were no significant differences among vendors. In comparison with Japanese MIBG study, there were some differences in LEHR condition. This is because Japanese MIBG phantom images were acquired with various imaging conditions, such as pixel sizes and acquisition durations. If an identical imaging condition is used, like MIVG phantom experiments condition in Taiwan, conversion coefficients would be feasible, would be stable even in different vendors. Next, conversion coefficients were compared among Taiwan, Europe, and Japan. Collimator types and the numbers were summarized in this table. We classified collimators into 6 groups. Interesting enough, low middle energy general purpose collimator was used in Europe and Japan, whereas extended low energy general purpose collimator was used in Taiwan and Japan. Here, I will summarize collimator characteristics. I summarize collimator characteristics using these collimator groups. The collimator characteristics are defined with 3 parameters: hole diameters, hole sizes, and septa thickness, and collimator length. Generally speaking, smaller holes, thinner septa, and shorter lengths are applied in LEHR collimator condition, whereas larger holes, thicker septa, and longer lengths are used in MELP collimator. Regarding the planar imaging condition, in Taiwanese and European studies, identical condition was used in all scans. However, various imaging conditions, acquisition durations, pixel sizes were used in Japanese study. This slide shows conversion coefficients in 6 collimator groups among Taiwan, Europe, and Japan. Red dots for Taiwanese data, green dots for European data, and blue dots for Japanese data. In LEHR condition, average conversion coefficients were similar among 3 areas. In LEGP condition, Japanese conversion coefficient was slightly higher. This is because various GP collimators were included in Japanese data. In LEGP, LMEGP, MEGP, and MELP collimator conditions, Taiwanese and European conversion coefficients were higher than Japanese conversion coefficient. How can we explain these results? Actually, there are 2 calibration phantoms, conventional types for Japanese study and lightweight type for Taiwanese and European studies. The weights are 3.8 kg for lightweight type and 6.3 kg for conventional type. Conventional phantom has 1 compartment for filling radionuclide. Lightweight phantom has 2 compartments for filling in radionuclide and water. The phantom structure difference will result in conversion coefficient difference. So, we assessed the relationship of conversion coefficients between Taiwan and Japan. This scatter plot this is a scatter plot of conversion coefficients in 6 collimator groups. X-axis is conversion coefficient in Taiwan and Europe. Y-axis is in Japan. So we could get a regression line of conversion coefficients between Taiwan and Japan. Japanese conversion coefficient is equal to 0.70 times Taiwanese conversion coefficient plus 0.20. By using this regression line, we can use Taiwanese and Japanese conversion coefficients interchangeably. Fortunately, Taiwanese and European conversion coefficients are compatible. If we compare HMR values derived from Taiwan and Japan, Taiwanese conversion coefficients can be converted into Japanese condition. Then we can get standardized HMR values using the following equation. In the next several slides, I will introduce the future direction of MIBG imaging and the evaluation of MIBG images. Here is our Monte Carlo simulation study of phantom imaging. The procedure of current phantom experiments is preparation of acrylic phantom, including radionuclide, then planar imaging using gamma camera. As compared with an acrylic phantom study, digital phantoms and density and source maps are generated from the X-ray CT images of acrylic phantom. Then Monte Carlo simulation allows to generate planar images using these digital phantoms. Moreover, we can easily modify collimator parameters, hole diameter, septal thickness, and collimator length. Then we can simulate under various collimator conditions. In this study, we evaluated the relationships between simulated conversion coefficients and collimator parameters in Monte Carlo simulation. These scatter plots show the relationships between simulated conversion coefficients and diameter, septal thickness, and collimator length. These results exhibited that conversion coefficients and collimator parameters showed non-linear relationships. We supposed if we used a machine learning model for this data, conversion coefficient estimation would be feasible based on the simulation results. So we used a gradient boosting machine learning algorithm, and the conversion coefficient estimation model was generated. To confirm machine learning estimated conversion coefficients, these conversion coefficients were compared with experimental and simulated conversion coefficients. Machine learning estimated conversion coefficient agreed well with experimental and simulated conversion coefficients in both LEHR and MEGP collimator conditions. What is interesting here is conversion coefficient for the standardization of HMR would be obtained without acrylic phantom experiments. Some researchers have been reported on HMR in MIBG SPECT images. In this research, volumes of interest were set on the heart and the upper mediastinum. Then SPECT HMR was calculated. Receiver operating characteristics curves exhibited planar and SPECT HMR have similar diagnostic performance. However, SPECT HMR is not common in the current evaluation of MIBG imaging. This is because SPECT HMRs have large variations in comparison with PRANA HMR. In these patient groups, coefficients of variation were higher in SPECT HMR than in PRANA HMR. To overcome this limitation, Dr. Nakajima and his colleagues developed AI-based organ segmentation method. In this SPECT images, volumes of interest for heart, left and right lungs, and the liver were clearly delineated. Furthermore, even in a patient who showed no MIBG uptake in the heart, cardiac volume of interest could be delineated on the heart. Scatter plots demonstrated that cardiac SPECT MIBG uptake showed good correlation with PRANA cardiac uptake. Moreover, cardiac SPECT MIBG uptake was also correlated well with PRANA HMR. The AI can support quantification of SPECT MIBG imaging. In summary, we can evaluate cardiac sympathetic nerve activity using MIBG HMR. However, HMR variations were occurred in collimators. To overcome these inferences, a dedicated MIBG phantom was developed for the HMR standardization. By using this phantom, multicenter MIBG phantom studies have successfully done in Taiwan, Europe, and Japan. Finally, we will interchangeably evaluate clinical HMRs among Taiwan, Europe, and Japan. Thank you very much.
Thank you, Dr. Okuda, for very clear and very practical use of phantom study using MIBG in Taiwan, Europe, and Japan. I see we do have two questions from the audience. The first question is, there is a movement from using standardization between different scanners from 2D acquisition to 3D imaging for improve the quantification. And what is your comment on this?
So thank you so much for the important question. As shown my presentation, some researchers have been reported on HMR in MIBG SPECT imaging instead of PRANA images. And I had experiments to quantify the HMR in SPECT images. The HMR values will be higher, and quantification, I think quantification is equivalent to the PRANA imaging. However, the variation of HMR will be increased due to the volume of interested setting in SPECT images. For example, cardiac region is mediastinal volume of interested setting is so difficult to manual operation. So in near future, so semi-quantitative or semi-automated and automated VOI setting will be required. Moreover, and Dr. Nakajima had developed an AI assist ROI setting algorithm. So by using the AI, the MIBG SPECT quantification will be more practical and widely used in MIBG study, I think.
Okay. I was just wondering, the standardized active value, I understand that some spec cameras actually can provide this kind of value, SUV value like PET. So, does that mean that the SUV value will also varies between different cameras if we use the spec technology to measure to do the quantification?
I think the HMR quantification like SUV variation will include even in quantification. This is because when identical collimator is used, the quantification is stable, but various cameras and collimators are used in quantification, the variation still remains.
Okay. One more question for me.
Okay.
Is there any differences for if we perform the CT attenuation or not using SPECT if we do the quantification?
Okay, and from the viewing of the quantification of MIBG uptake in cardiac, attenuation and scatter corrections, both corrections are needed to get true values. I think
maybe even motion correction will be needed.
Yes, for sure.
Yes. We have one more question from the audience. Does the CCT detector, such as the CT whole body SPECT, be more suitable for iodine 123 behind MIBG scan?
Well, the CT detector such as CT whole body SPECT can be suitable. The answer is yes. Dr. Nakajima and his colleagues and MIBG quantification in this SPECT and CCT camera by using planogram images and HMR quantification has been performed.
Yeah. Okay. Because of the time constraint, I think we will have to stop this session at this time. But we thank Dr. Okuda for the wonderful and very clear speech on using the phantom study in Taiwan. And hopefully we could continue to use this kind of calibration across all the cardiology and neurological studies. Okay, thank you, Dr. Okuda.
Thank you so much.